During summer vacation, you've offered to care for your younger cousin 1 day a week. You always like to take her to the park in the morning before it gets too warm outside. Your cousin really likes singing in the cylindrical plastic tunnel at the playground. She likes the way her voice sounds inside the tunnel. As a young physicist, you know this is because of resonance. When your cousin sings Let It Go, there are two particular notes. So there are two particular notes where the sound becomes larger or louder. So that means there's two specific frequencies that we are looking at for resonance. When your cousin lies down in the tunnel, she's the same length as it, which you know is 1.2 meters. So again, this is something we need to highlight as it will help us solve the problem. A thermometer installed at the park tells you that the air temperature is 23 degrees Celsius. We're going to need to know this to figure out the wave speed as we're looking at sound waves, and you can determine that speed through temperature and a formula for it. Assuming that the notes your cousin is singing are the first two resonant frequencies, okay, for this air column, which frequencies is she singing? So we're supposed to figure out the frequencies, specifically two separate frequencies, and those two frequencies are for the first two modes or harmonic of the standing wave. Now we know there's a standing wave because when you have resonance, it creates a standing wave. Okay, so that's why we can assume from the context of this problem that we're working with standing waves, and also we're being asked to draw standing wave diagrams here, which we're going to do now. Before we draw the standing wave diagram, it's important to understand the different components that go into building the diagram. And those are nodes and antinodes. Nodes are fixed points with zero amplitudes and no motion, whereas antinodes are points with maximum amplitude. So we will start by drawing the first harmonic's standing wave. This is how the diagram looks like for the first harmonic. Since the wave is in a tunnel, it means that both ends of that tunnel must be open end. Now, when you have that specific boundary condition, this is how the pattern looks like for the first harmonic, where you're going to have two antinodes at both ends of the wave and one node in the middle. The length of the standing wave must be the same as the tunnel. So in this case, that would be 1.2 meters. And it does not change. I repeat, it does not change throughout the new modes that you're going to add. So this is an illustration for the second harmonic standing wave diagram. In a system with two open ends, higher harmonics form by adding node and antinode pairs between the open ends, which you can see through the inclusion of this node and this antinode, which were not previously seen within the first harmonic. It's also important to note that, as always, the length remains the same, and because of that, the actual amount of boxes between your first antinode and your final antinode must remain the same, because that is what we are using to model the length. So in this case, I have 1, 2, 3, 4, 5, 6. 6 boxes that I use from the first antinode to the final antinode within my first harmonic. Therefore, in my second harmonic, I should also have 6 boxes between my first antinode and my second antinode, which I do. The next question states, describe the motion of the sound wave. Include a motion representation as part of your explanation. It's important to note that you do not get confused between the motion of a sound wave and the motion of the particles within the wave, because both of those motions are separate from one another. In this case, it's asking us for the wave's motion, so let's start analyzing that. When the sound wave is initially produced, the wave moves away from the singer towards the end of the tunnel. It then reflects back towards the singer at the same speed. This means that the direction flips. Therefore, you cannot have constant velocity because the direction is changing. However, we do have constant speed because the speed remains the same throughout the whole motion. The position time graph was also meticulously thought out. Since the distance to the open end of the tunnel is the same as the distance back, we're going to have same distance going away and returning. You also have the same speed because the wave speed does not change unless a physical medium changes, which is not the case. Therefore, we have the same time for the wave when it's moving away from the singer and when it's coming back towards the singer. And because of that, we need to ensure that the total amount of time from event 1 to 2, which represents moving away from the singer, is the same as 2 to 3, which represents it coming back. And so in this case, it's 4 blocks, because if you notice, I have 1, 2, 3, 4 blocks from event 1 to 2, and the same amount from 2 to 3. And since this is the axis for time, it all works out. Positive direction within our position time graph is denoted as moving away from the singer, and we know that because of this notation. Therefore, from event 1 to 2, we are moving away from the singer, and that's because we're moving upwards, which is positive direction. And the opposite is true from 2 to 3, as we're moving downwards, which is negative direction, and the opposite direction would be moving towards the singer. Another thing to note is that the slope is going to be linear, or it's only going to be one specific value. And that's because the slope is the velocity, which includes the speed. And since the speed is constant, our slope must remain constant. It cannot change and become a curve, because that would mean we have a non-uniform speed. The next question asks us to describe the motion of the air particles as the sound wave passes by them. So in this case, the particle will oscillate back and forth, and it will do this either away or towards the singer. It's also important to note that the motion is parallel to the direction of the wave, and the reason for this is because the sound wave is longitudinal. If it was a transverse wave, then you would have a perpendicular motion to the direction of the wave. Alright, next up, we'll start our math representation. To start, we're going to find the speed of the sound. And the reason for this is we're looking for frequency. And the way you would find frequency is through this formula here, right? And for this formula to work, we need wavelength and speed. Now the wavelength will differ within the different harmonics, but the speed will remain the same. So doing that first will be beneficial, as we're going to use that same value throughout our next calculations. This is how you solve it. You want to use this formula here, which is the formula to find the speed of sound. And in that, you want to substitute in 23 degrees Celsius for the letter T, or the variable of T, which is our temperature. And once I do that, I get this value back, which is our wave speed. As I said before, to find frequency, we need the speed, which we have, but we also need the wavelength, which is represented through the Greek symbol of lambda. So the next thing we will do is find the wavelength for the first harmonic. The next step is finding the frequency for the first harmonic, and we do that through this formula. It's called the universal wave equation, and specifically we are supposed to isolate for the frequency. So we're going to be dividing this by the wavelength, and since we do that on one side, we have to do it on the other side. And once we do that, we get frequency, which is equal to speed over the wavelength. And then we can just divide those two things, and we get our final answer of 143.57 hertz. That's for the first harmonic, though. We need to now find it for the second harmonic, so we have to repeat these two steps again. We don't have to repeat this step again, because remember, the speed will remain constant. These are the two final steps into completing this problem. The first one is finding the wavelength of the second harmonic, and then using that wavelength to find the frequency. We already have speed from before. So to find the wavelength, all you need to do is use this equation. For the second harmonic, the length equals the wavelength itself. So all you need to do is substitute in the length, which we know to be 1.2 meters, and that we can say is equal to wavelength. Then we use that within the universal wave equation, and specifically another form of this equation, which we have determined through step 3, where we will be dividing the speed by the wavelength to find the frequency. So we already know speed, and then we just divide it by the wavelength, which we got from step 4, and then now we have the frequency for the second harmonic. both calculations for the first frequency and second frequency have two significant digits. And that's because if you look in the actual substitution, the least amount of digits are 2, from 2.4 in this case and 1.2 in this case. So to denote two significant digits within these two values, we can use scientific notation. So this is the final answer that you can write within a therefore statement. That way your teacher knows exactly where to look for within the final answer. We're finally on the evaluation. Within the evaluation, there are three different components, which just help us make sense of a specific answer. In my case, I'm looking at F2, or the second frequency. So, first of all, we need to see if the size makes sense. And it does, because it must be bigger than the first frequency, as we're moving on to the next harmonic. The second thing is direction. Now, the direction must always be positive in the sense that the sign of these values must be positive because there's a scalar value. In reality, there will be no direction. Then we have our units. Within our units, we just look at the way we've set up our equation, and that comes from here, right? So we just take those units and we do unit analysis, where we basically use mathematics to basically manipulate these units to get our final answer. So in this case, we are doing meters over second, and we're dividing that by meters. Now that's the same thing as multiplying meters over second by 1 over meters. And I think that's much easier to understand, because that way you can clearly see how the 2 meters are being canceled out. Afterwards is just 1 over seconds, which is equivalent to hertz. And that makes sense because our answer is a frequency, and frequency's unit is hertz.